Let's continue our discussion of calculating theoretical probabilities in the next few examples. Example 3. Suppose I flip two identical coins. What is the probability I get two heads? Let's put the formula we learned in example 2 to practice. The probability of an event, such as getting two heads, should equal the number of favorable outcomes divided by the total number of possible outcomes, as long as each outcome of the experiment is equally likely. In order to find either of these quantities, we might first make a list of possible outcomes. One such list might note that the possible outcomes for flipping two identical coins include getting two heads, getting two tails, and getting one head and one tail. If we were to use this list of possible outcomes and the formula from example 2, we might calculate the probability of getting two heads to be 1 out of 3, or 1/3. Unfortunately, our answer would be incorrect. The problem is that the outcomes in our list are not all equally likely. This is because it is twice as likely to get one head and one tail than it is to get two heads. To formulate a list of equally likely outcomes, the textbook recommends imagining that the coins are labeled in order to distinguish them. That is, even though our experiment involves two identical coins. Let's assume for the moment that one coin is a nickel and the other is a penny. Using labels to distinguish the two coins forces us to consider the outcome in which the nickel lands on heads and the penny lands on tails, and the outcome in which the nickel lands on tails and the penny lands on heads as two different outcomes. Consequently, we get a list of 4 possible outcomes, one of which the nickel and the penny both land on heads, one in which both coins land on tails, one in which the nickel lands on heads and the penny lands on tails, and the last of which the nickel lands on tails and the penny lands on heads. Note that both of these lists are ways of expressing all possible outcomes of this experiment. However, in the second list, all the outcomes are equally likely. Therefore, when calculating the probability using the probability formula found after example 2, it is important to use the second list of outcomes. This means the probability I get two heads is equal to the number of favorable outcomes, 1, divided by the total number of possible equally likely outcomes, 4. The probability of 1/4 can also be expressed as 0.25 or 25%. Example 4. Suppose we toss a pair of standard 6-sided dice. What is the probability that we roll a sum of 6? That is, the sum of the two faces is 6. Recall from above, in order to use the probability formula given after example 2, we need both the number of favorable outcomes and the total number of possible outcomes, where all outcomes are equally likely. A common list of outcomes for this experiment is as follows. We might roll a sum of 2. This would involve both die rolling a 1. A sum of 3. This would involve one die rolling a 2 while the other die rolled a 1. A sum of 4. This might involve both dice rolling a 2, and so on. Note that if we use this as our list of possible outcomes, there are 11 outcomes, one of which is favorable. So we might conclude that the probability of rolling a sum of 6 is 1 out of 11. Unfortunately, once again, this is not correct. Just like our original list of possible outcomes in example 3, this list includes outcomes that are not equally likely. The problem is, there is exactly one way to roll a sum of 2. both die need to show a 1. On the other hand, there are many ways to roll a sum of 7. For example, one die might be 2 while the other is 5, or one die might be 1 while the other is 6. Because of that, we cannot use this list when calculating the number of possible equally likely outcomes, which is needed to use the formula above. As we discussed previously, in order to find an exhaustive list of equally likely outcomes, it is helpful to distinguish the dice. Let's imagine that one of them is red and the other is green. There are 6 possible outcomes for the red die, 1 through 6. And for each number on the red die, there are 6 possible numbers for the green die. That is a total of 6 times 6, or 36 possible outcomes. We might get a 1 for the first die and a 1 for the second die, which would give us a sum of 2, or a 1 on the first die and a 2 on the second die, which would give us a sum of 3, and so on. After I complete my chart showing all possible outcomes and their sums, I notice that there are 5 ways to roll a sum of 6. Since we are trying to find the probability of rolling a sum of 6, these are our favorable outcomes. Thus, the probability of rolling a sum of 6 is equal to 5 over 36. We could keep this as a fraction, or if you would prefer, you can express this as a decimal or a percent. Example 5. Suppose I pick a jelly bean at random from a box containing 3 red and 2 blue ones. I record the color and put the jelly bean back in the box. What is the probability of getting a blue jelly bean both times if I do this twice? Once again, in order to use the formula found after example 2, we will need to find the total number of possible equally likely outcomes, as well as the number of favorable outcomes. One list of possible outcomes is as follows. I could pick 2 blue jelly beans, or 2 red jelly beans, or 1 red and 1 blue jelly bean, or 1 blue and 1 red jelly bean. Using this list of possible outcomes and the formula from example 2, I might conclude that the probability of getting blue both times is equal to 1 out of 4, or 1/4. But this calculation does not take into account that there were more red jelly beans than blue ones. In fact, because of this inequality, we are more likely to get a red jelly bean both times than we are to get a blue jelly bean both times. Consequently, the outcomes in this list are not all equally likely. In order to create a list of equally likely outcomes, let's use the same strategy we used in example 4. In example 4, we created a matrix in which the rows represented the possible outcomes associated with the red die, and the columns represented the possible outcomes associated with the green die. In example 5, let's once again create a matrix, but here the rows will represent the possible outcomes associated with the first pick, and the columns will represent the possible outcomes associated with the second pick. Let's also use labels to help us distinguish the red jelly beans from one another. If we do the same for the blue jelly beans, we will create a list where every outcome is equally likely. Once we use labels to distinguish both our red and our blue jelly beans, we notice that there are 5 possible outcomes for the first pick. Moreover, since we put the jelly bean back in the box between the first pick and the second pick, these same 5 equally likely outcomes also represent the possibilities for the second pick. That gives us a total of 5 times 5, or 25 possible outcomes for the entire experiment. For example, we might get the first blue jelly bean on the first pick, as well as the first blue jelly bean on the second pick. Or, we might get the second blue jelly bean on the first pick, and the first red jelly bean on the second pick. Or, we might get the second red jelly bean on the first pick, and the first red jelly bean on the second pick. and so on and so on. Now, we've been asked to find the probability of getting a blue both times. According to our list, there are 4 outcomes in which we get a blue jelly bean twice. These are what we refer to as our favorable outcomes. Thus, the probability of getting a blue jelly bean twice is equal to 4 out of 25, which of course can also be written as 0.16 or 16%. Note, you may have noticed that the probability of getting a blue jelly bean 2 times, which we found to be 4 out of 25, is equal to the probability of getting a blue jelly bean for our first pick, 2 out of 5, multiplied by the probability of getting a blue jelly bean for our second pick, 2 out of 5. This occurs because the 2 events are independent. That is, selecting a blue jelly bean on the first pick does not affect the probability of selecting a blue jelly bean on the second pick. In general, if 2 events are independent, that is, the one occurring does not affect the probability of the other occurring, the following holds. The probability of event 1 occurring and event 2 occurring is equal to the probability of event 1 occurring times the probability of event 2 occurring.